How's it going, ladies and gentlemen? Mr. Downey here, going over 9.4, 9.5 problems, which have to do with covalent bonding and orbital overlap and hybrid orbitals. So 13 says, according to the valence bond theory, which orbitals overlap in the formation of the bond between H and Br? So what's going to happen in this theory is that the valence electrons simply overlap. So if I had like an H atom, well, here's its 1s orbital, and here's another hydrogen. When they're forming H2, what they're saying is the bond is just an overlap of those orbitals, right? So if we're looking at HBr, well, we got to look at the configurations of H. Well, we know it's 1s1, that is its valence electron, so that is going to be 1s. And we look at, well, what about Br? What orbital is being filled for Br? And you could just kind of look on the periodic table. I don't think I got it pulled up, but I will do it right now, right? Periodic table. And if you remember the electron configurations for the things that are getting filled, Br is in the p block and the fourth period. So we're filling the 4p valence shell for Br. So it's going to have to be choice A because those are the valence shells for their elements. 14. According to the valence bond theory, which orbitals overlap in the formation of an N2 bond? Again, so you're going to go, well, what is the valence shell for N2? Well, I see N over here. It's in the p block of the second energy level, second period, so second energy level. So we're looking for 2p. So that would be choice D, as in David. 15. In which of the following molecules does the central atom utilize d orbitals to form hybrid orbitals? All right, so when we're hybridizing, the first one that we hybridize is we put in that 1s orbital. Then we start to put in p orbitals, right? We have 3 to put in. Only after adding that 1s and the 3 p's together do we get to the d sublevel. So we're talking about at least 1 plus 3 plus 1, at least 5 domains. So which one of these molecules needs at least 5 domains around that central atom? Well, PCl3 looks like this, with a lone pair of electrons, so there's only 4 domains there, so it can't be that one. CCl4 is going to look like this. So again, it only has 4 domains, which means it would be sp3. So not what we want. TeCl4, central atom, is going to look like this. So we have 5 domains. We got 4 bonding to chlorines and then 1 for the unshared pair of electrons. So we got 5 domains. So this one definitely will use that, and it is sp3d hybridization. XeF2 is going to look like this. I'm sorry, F4. Oops. And how many domains does it have around the central atom? Well, 4 for bonding and 2 for non-bonding. So we got 6 domains, which means it would be sp3d2 hybridization. So definitely that one as well. And SF6, I'm not even going to draw that. You can just go, well, there's at least 6 bonding domains. In fact, there's a total of 6. So would it be sp3d2? And that one as well. So which one gives us that? 3, 4, and 5, choice D. 16. The electron domain geometry of a carbon-centered compound is tetrahedral. The hybridization of the carbon central atom is blank. So if it's tetrahedral, we know we have 4 domains. So how do we get 4 domains? Well, we're going to need 1 s and 3 p's. That's like taking, well, we have the s and the 3 p's, and basically what we're doing is we're hybridizing them to give us 4 equal orbitals of sp3 hybrid orbitals. So that's it, choice C. 17. Of the following, only blank has sp2 hybridization of the central atom. So we're talking about 3 domains. So we're going to have to draw them out and see what it looks like. pH3, hopefully you've seen enough times to have an idea that it looks like this. So it's got 4 domains, so it can't be that one. CO3 minus 2 is going to look like this. And it has 3 domains. That's awesome. So maybe it's B. Let's keep checking them all. ICL3 is going to look like this, and it's going to have 5 domains. So nope, not that one. I3 minus is going to be like this. It's going to be a linear molecule with 5 domains around it, so not what we want. And then PF5, you should know right off the bat, well, there's going to be more than 3 domains, so definitely not. So choice B. 18. Hybridization of oxygen atom, labeled Y and the structure below is blank, and the COH bond angle is blank. All right, so we're looking at this one right here, and then we're looking at the COH, this right here, the bond angle here, around that oxygen. So if I were to redraw it, it's going to look like oxygen, 2 lone pairs, H, and then to the C, and then the rest of the molecule over that way. Well, what is this angle? Well, first we got to say how many domains are there? Well, there's 1, 2, and then 3, 4. So 4 domains means we must have 4 hybrid orbitals, and we get that by doing sp3 hybridization. Okay, well that also tells me that it's a tetrahedral shape, which has a bond angle of 109.5 degrees. So there's my answers, sp3 and 109.5. So choice, where did my thing go? Choice C. And last one for this section, valence bond theory does not address the issue of blank. Well, it doesn't address the excited states of molecules. All right, we've talked about atoms getting excited and absorbing and emitting light, but we haven't talked anything about molecules. So this actually has not been addressed yet, and that'll be addressed when we talk about molecular orbitals. That'll be where we talk about excited states of molecules. It talks about molecular shape. It talks about covalent bonding. It talks about hybridization and multiple bonds. It talks about all those things, just not A. All right, ask questions in class. I'll see you there. Deuces.